Hey, I like doing physics problems, so I'm going to do 4 of them. I like uniform circular motion. Something really, not magical, but I just love this idea that our mathematical models, and just some very simple calculus, just have to know some very basic trig stuff, that there's this perfect amount of acceleration pointing toward the center of a circle that will change something's velocity just in the right way so that the magnitude won't change, but the direction will change, and it will just travel around at a constant speed in a circle. I just love that. It's all around us, uniform circular motion. What is the magnitude of the acceleration of a sprinter running at 10 meters per second? When rounding a turn of radius 25 meters. And what do they want to know? What's the, well, I guess there's not much to do here, is there? The acceleration of the centripetal variety is v squared over r, so that would be 10 squared over 25, which is mostly 4. And yeah, not much else to say about that. And of course, pointing toward the center of that circular path. 64. Particle moves horizontally in uniform circular motion over a horizontal xy plane. Look at me drawing my xy plane. At one instant, it moves through the point at coordinates 4, 4. There it is. And with a velocity of negative 5I. So let's see, negative 5I. Now, if you're looking at this and saying, oh, wait a minute, how come you didn't make that go like further? But the scale of this is my xy plane in meters, right? This is x position, this is y position in meters. So when I draw the velocity, and the velocity has different units, that's meters per second, so I'm under no obligation to stick with the scale here that I have. So in the negative I direction, it is going 5 meters per second. And it has an acceleration of positive 12.5 j. Same thing. I don't have to stick with the same scaling. I don't have to make it look 2.5 times bigger than this because it has different units. Acceleration is in the positive j direction. Meters, 12, there's a number there, 12.5 meters per second squared. Okay? What are the x and y coordinates of the center of the circular path? Well, the center is up here somewhere. So this is mostly about just understanding the relationship between this velocity and acceleration vector. So if this thing's going this way, then that's tangent to the path. And if the acceleration is pointing this way, well, then the center is somewhere up here. So the circular path, there's only one possible way we could construct that circular path. Sorry, with apologies to number 62 for intruding on its space. Right? Because this is pointing toward the center, and this is pointing in the direction it's going, tangent to the path. So, all right, if I know what the A and the acceleration and the velocity are, I know that centripetal acceleration is v squared over r. So r is equal to v squared over a, which would be here 5 squared over 12.5, which is 2 meters. And I know that that center must be up here. So the center has to be 2 ticks up in the y direction. So it would have coordinates 4 meters and then 6 meters. 2 meters up from there. This is not to scale, so sorry about the gross exaggeration of that 2 meters. And did they ask that as an A, B? Yeah. So x coordinate, answer to part A, answer to part B. Alrighty. That picture sure helped a lot, didn't it? It'd be hard to do without that, I think. 66, particle moves along a circular path over a horizontal xy coordinate system at a constant speed. Okay. Throw those down. Time t1 is equal to 4 seconds. It's at the point 5, 6. Okay, so make another point here. It's 5, 6. There it is. This is happening at time t1 is equal to, is it 4 seconds? All right. And it has a velocity of 3 in the j direction. If you didn't get this one, and you're like, oh, okay, that makes sense now, then you really, and I presume if you didn't get that one, you probably didn't get 66. So if you didn't, this is the place where you need to pause and say, okay, I'm going to try 66 now, right? Take the training wheels off. Do it yourself. If you just sit there eating popcorn watching these videos, it's really not the way it's supposed to work. 3j all right, and the acceleration is in the positive x direction. So the acceleration is this way, but they're not telling me how much. Okay, so just like this one, this has to be the center of the circle is somewhere over here because acceleration points toward the center. So it must be going this way, like that, around the circle in the clockwise direction. At time 10, it has a velocity of -3 and acceleration in a positive y direction. Okay, so at time 10, it has a velocity of -3i. So a velocity of -3i. A velocity of -3i. That's this way, right? Now, we already know that it's going around this way, so the only place that it could have a velocity of in the negative I direction is down here, because the velocity has to be pointing in the direction of the path. So that has to be here. And that's at time 1, time 2 rather, is equal to 10 seconds. And they said that the acceleration is pointing in the positive y direction. They actually didn't need to say that. We could have figured that out. That is bonus information for us. All right, and of course it's uniform circular motion, so the speed is still 3. And they would like to know, what are the x and y coordinates of the center of the path if this is happening in less than 1 period? Well, this happened took 6 seconds from time 4 to 10 to get 3/4 of the way around the circle. Right? So that means 6 seconds is equal to 3/4 of the period. Now, maybe you just look at that and you're like, oh, well, it's 8 then, right? Because 2 seconds, 2, well, however you think about that. But you can write an equation like this, and if it's some like really awkward segment of the circle, or it's not an easily divisible time or something like that, you can always set up an equation like this and actually just do math. So the period is 8 seconds, and we needed that because I know that v is equal to 2 pi r over t, which means that the radius of the circle, which is I think what we need to know, is equal to VT, you Virginia Tech fans out there, over 2 pi, and you better put that in parentheses in your calculator. So that's 3 times 8 over 2 pi. So my trusty calculator says that that is equal to 3.82 meters. So where's the center of this? Well, this was 5, 6 right here, right? So the center is, it's over this way. The y-coordinate is the same, and the x-coordinate is 3.82 meters to the right of that. And that's going to be 8.82 meters. Right, and I think they asked that, yeah, they asked where this is part A and part B. Right? Aren't these problems fun? Number 68. This is really very similar again. So if this is all starting to make more sense to you, then go ahead and hit that pause button. A cat rides a merry-go-round. Okay, they lost me. That's so unbelievable. Cats don't ride merry-go-rounds. Turning with uniform circular motion. At time 2, the cat's velocity is 3I4J. All right, I'm just going to sketch that vector. So this is the velocity at time 2 is 3I4J. 3, 4, and for those of you who are fans of Pythagoras, you might recognize that the speed then is 5. So it's kind of like that direction. I don't want to pin that onto a circle yet because I don't know. I mean, at some point, maybe I'll draw it over here. We can have a circular path. But just knowing this, there's actually, if I don't know what direction it's going around this circle, there are 2 places that you could pin this velocity onto this. You could pin it on here if it was going clockwise, or you could pin it on over here if it's going counterclockwise. I think I said that clockwise and this way. No, that's right. That's counterclockwise, yeah. So it could be here or here. Unknown at this point. And let's see what else we have. So I do know the speed, though. The speed's 5. Measured on a horizontal x-coordinate system. At time 5, the velocity is -3, -4. So that's going to look like -3, -4. Of course, it has to have its uniform circular motion, so it still has a magnitude of 5, but now it's pointing exactly in the opposite direction to that one. Okay, so where could that be pinned on? Well, it's exactly on the opposite side of the opposite. That's what you get if you put opposite and side together. It's a portmanteau. I like that. I'm going to use that in the future. So it's exactly opposite to this. But we still don't know which one is right because I don't know which direction it's going. So one is here and the other is here, or vice versa. What are the magnitude of the cat's centripetal acceleration and the cat's average acceleration during the time interval? So we don't know which way, but presumably we're going to get the same answer for either one. So I'm going to go ahead and say that we are going this way, and then we can ponder when we get our answers and think about whether they would be the same or not for these questions. The magnitude of the acceleration, well, that doesn't depend on which way we're going. The magnitude of it, it's still going to be the same amount of acceleration toward the center. So sure enough, that's not going to depend on this. So let's see. To do that, Well, what other information do I have? If this is halfway around here, so it looks like the period is 6, right? Because 1/2 of the period was 3 seconds, so the period must be equal to 6 seconds. And I know the V, so that means, just like we did here, my R is Virginia Tech over 2 pi, which is 5 times 6 over 2 pi. That's 4.77 meters. That's the radius of the circle. Sounds pretty reasonable for a merry-go-round, I guess. Not that this is a reasonable problem, because there's a cat on it. So now I think we want to find the magnitude of the centripetal acceleration, which is v squared over r. So that's 25 divided by 4.77. It's about 5.24 meters per second squared. I do believe that is the answer for part A, yes. And part B, what's the cat's average acceleration? I don't know why. I guess because we get used to doing these like calculus type things and talking about instantaneous accelerations. We tend to forget. My experience is that students often forget when we talk about average something, this is true for calculus and physics, that we're talking about like an actual slope calculation, or with vectors, an actual difference. Right? So here, average acceleration is that's actually 5, sorry. The velocity at 5, that's like my final, minus initial, over 3 seconds. And you have to do this by components. You have to say, oh, it's 5 minus 5, that's 0. No, not true. You have to do it by component. So I'm not going to leave out any steps here. So the velocity at 5, that was -3, -4. -3I minus 4j meters per second, minus +3I +4j meters per second. Sorry, a very small insect just flew into my eye. Over 3. So -3 minus 3, that's minus 6I, minus 4, minus 4, and then that's over 3. And this is an acceleration. These are in meters per second. This is in seconds, so that's going to be meters per second squared. It's not a huge problem leaving it like this, but we really should just divide through by the 3 there. And sorry, I'm trying to conserve the paper space here, so I'm kind of working my way up here. Not recommended. So that's -2I minus 2.67j meters per second squared. But I think that they asked for the magnitude. Yeah. So we just have to Pythagorize that. So what is the square root? You know that you can use absolute value signs to do magnitude with vectors, that means the same thing. It just means like what's the size of it, the absolute value. That would be the square root of 2 squared plus 2.67 squared, which is 2 squared. I can't believe I just typed in 2 squared into my calculator, like I didn't know it was 4. Wow. 3.34, looks like. That is the magnitude of the average acceleration, which is not going to be equal to the centripetal acceleration. All right. Was that from this problem? Yeah. Yeah, that was the answer for part A. Okay, that's all.